Hello, I am recording a little follow-up to that lecture meeting. I apologize. I now have my computer and can draw. And I wanted to spend a little time going over pH again, just to give you a little bit better of an understanding. I'll try to make it quick. But I realized that a concept that might be helpful when thinking about pH is thinking about what concentration, oops, that's interesting. Thinking about what concentration means. And like when we're talking about concentration of water, what the concentration of hydrogen means relative to that amount of water. This is the least attractive beaker. Let me get my, let's see if I can get my drawing tablet like oriented differently to my hand so that things come out looking more like what I want them to. Okay, nope. This is a this is a beaker of water, say. It is a liter, so you can think about a 2-liter soda bottle is 2 liters. This is about half that size. Let's say it has water up to here. So this amount right here is 1 liter of water. So, so liter, when we talk about liters, liters are a measurement of volume, meaning, you know, like how much kind of space or area something fills. When we talk about moles, moles are a measurement of the number of actual molecules of water that are in something. So let me make this water. Isn't it funny that we always draw water blue? Really, it's like clear, but we need it to, glass is clear too, so it has to be something. Okay. I guess sometimes it looks blue because of the way light bends through it or something. I don't know. Let me make this bluish. All right, that's kind of ugly, but whatever. So, go back to my pen, go back to the black. Okay, so 1 liter of water, and I'm just going to tell you this from the internet, has a concentration. No, not a concentration. Let's just say a number of water molecules in it. If you could zoom in to the teeny tiny H2Os that were in here, if you counted all of them, you would count 55.5 moles of water molecules in 1 liter of water. Scientists just know that because they figured it out in an experiment somehow at some point or something. I don't know, it's a number I got off the internet. So I'm just telling you it's true. There are 55.5 moles of water in 1 liter. That means that water has, that the concentration of water molecules here is 55.5 moles per liter. And we have another unit that we use to describe that, which is capital letter M. Big M means moles per liter. So we could say the concentration is 55.5 molar, we would say, or has 55.5 molarity. But 55.5 big M means there are 55.5 moles of water molecules in this liter. Sorry, my dog is farting. I don't know if you can hear that. Thanks, Goose. Soundtrack provided by Lucy. And then as a reminder, a mole is a term that means kind of like a dozen, but it's a different number than 12, but it's, you know, it means like a certain quantity of water molecules. So 55, so if we wanted the actual number of water molecules, we would say 55.5 moles times there are 6.02 times 10 to the 23rd molecules per mole, I guess we could write. Basically, you would just multiply, right? Just like if I said how many eggs, if you had 55 dozen eggs, you would say, well, that means 55 times 12 eggs. If I say you have 55 moles, then you say 55 times 6.02 times 10 to the 23rd, oops, pretend that's a line under there, moles. And you would end up with, what is that, 55 times 6 would be like 300. You'd end up with something like 3 times 10 to the 25th. So that math could be wrong, but it doesn't really matter too much right now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There are approximately this many molecules of water in 1 liter of water. It's a lot, right? Okay, so now you know how many molecules of water are in here. When we're talking about pH, what we care about is how many molecules of hydrogen are in this same liter. And the reason that pH, that we care about that so much, the reason that pH is so important, remember that hydrogen is the first element on the periodic table. So it has 1 proton, 1 positively charged molecule in its nucleus. Sometimes it has a neutron, sometimes it doesn't. Usually it doesn't, I think. Hydrogen, as it's shown on the periodic table, not H+, but just plain old H, would have 1 electron. But when we're talking about hydrogen with a plus on it, like this, some other element has stolen that electron away, doesn't have it anymore. All it has now is just the proton. Oops, I erased part of the plus. And that proton, because it has that positive charge, it likes to interact with other molecules, and it can be involved in a lot of different chemical reactions. And so it can really affect the way that the liquid behaves, basically. So something with a lot of positive charges is really acidic. And something with not very many positive charges, it actually is going to have a lot of this, which has that negative charge, and that negative charge also wants to react with things. And so having a lot of OH minus or having a lot of H plus makes a liquid very reactive. So really acidic or really basic things can be very like caustic, or I think you call it caustic when it's basic. I can't remember. And I don't remember what you call it when it's acidic. It's acidic, but it, like, you know how like acids like degrade things? That's partly because like it can just engage in all these chemical reactions. Okay, so let me erase some of this. So let's talk about the concentration of hydrogen. My screen's dirty, so sometimes I'm trying to erase like dirt on my screen, and it's not erasing, believe it or not. Okay. So, okay. So again, concentration is the amount of something that's in a certain volume of that thing. So like if we said that there were 55.5 moles per liter, that's concentration because it's amount per volume. When we talk about pH, it is related to the concentration of hydrogen, meaning it's related to how much hydrogen is in a certain volume of liquid. So there are 2 formulas, and I always have to think about which one is which. Hold on. I also realize that sometimes I have a hard time remembering formulas off the top of my head while I'm trying to lecture, because I'm used to having lecture slides to be my memory for me, and now I'm just doing it off the top of my head. So anyway, okay. So this is my favorite formula, is the one on the bottom. Concentration of hydrogen is equal to 10 to the negative pH. And if I put a unit on this, it would be moles per liter, or molarity. Because remember, concentration, and these square brackets mean concentration. Concentration is an amount per volume, and usually we talk about it in terms of moles per liter. So let's say in this whole liter of water, let's say this liter of water has a pH of 7. it's neutral water. Pure water should be pretty neutral. So, okay, so what we do is we say, well, we know what the pH is. Maybe we use like a pH strip or a meter or something to find it out. We can take that number 7, we can plug it into this formula right here, and that will tell us how many moles of hydrogen are in this solution per liter. So concentration of hydrogen equals 10 to the negative 7th. That means 1 over 10 to the 7th, because remember that negative sign acts like a little elevator button and it pushes it down to the bottom floor. So there are this many moles of hydrogen per liter of water. And if we were to kind of, you know, spread that out a little bit more, we would say 1 times 10 to the 7th is 1 with 7 zeros, 4, 5, 6, 7, boop, boop. Or what is that? 10 to the negative 7th, 1, 2, 3, nope. 1, 2, 3, 4, 5, 6, right? I think. I get mixed up on this stuff sometimes too. So there are this many hydrogens, moles of hydrogen. There are this many moles of hydrogen per liter of water. So there's 55.5 moles of water. There's a teeny tiny fraction of a single mole of hydrogen in this whole liter of water. So again, remember we spelled out that number and it was like 3 with like 25 zeros after it, molecules of water. Let's see what this would be. If we said, let me make some room here. Eraser. Okay, I'm gonna erase, I didn't even write that formula yet. If we said there are, let's say 1 over 10, well, no, we can just write it the way, okay. So we plugged in negative 7 into the formula. We said that that was 10 to the negative 7th moles, right? And so that many moles, so how many molecules is that? We multiply it times 6.02 times 10 to the 23rd to go from moles to molecules. And remember our math rules, these have the same base, so we can just add the exponents. So we end up with 6.02 times 10 to the, what would that be, 16th. So 602, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's how many molecules of H plus are in 1 liter of water. So even though it's a tiny fraction of a mole, it's still a large number of molecules. But remember that when we wrote out how many molecules of water there were like twice as many zeros. So like the number goes like 3 within like zeros all the way to here. So it's a tiny fraction of the number of, so there's like, you know, some little H pluses floating around in here, but there's a heck of a lot more water compared to the amount of H plus that's in there. Okay. So let me erase some of this again. So I'm basically just trying to help you understand like what pH means. pH is, it gives us a sense of, instead of thinking about, oh, there's, you know, 602 kajillion hydrogen molecules in this liter of water, we can just say the pH is 7 and, oops, hold on. And that gives us like an easier frame of reference for what that means in terms of a liquid. Hold on. So back to the different pHs. So normally, and I totally lied in lecture when I said that a pH of 1 or pH of 0 meant I was confused on what concentration. It was nonsense. I'm going to show you what the different pHs mean. So normally we have a scale that goes from, usually we talk about like 1 to, wow. Okay, if that doesn't tell you where my brain's at, 3 comes after 2, 4, 5, 6, 7, 8, 9, 10. Usually we go all the way down to like 14. We go from 1 to 14. I don't know why that is exactly, because pH can keep going in either direction. You can even have negative pHs. So we just did concentration of hydrogen for pH of 7 equals 10 to the negative 7th. So for pH of 6, the concentration of hydrogen is 10 to the negative 6, and so on. Let's start here with 10 to the 1. So if the pH is 1, which is very acidic, then we're saying the concentration of hydrogen equals 10 to the negative 1, which equals 1 over 10, which equals 0.1 moles of hydrogen per liter of solution, okay? So remember that 0.1 moles is still a lot of molecules, because you would do 0.1 times 6.02 times 10 to the 23rd. So it would end up being, and I'll just trust me on the math here, that it would end up being 6.02 times 10 to the 22nd. So imagine that 6 with 22 zeros after it. That's how many molecules of water, of hydrogen, you would have in 1 liter at pH 1, okay? So here, concentration of hydrogen would equal 10 to the negative 2, which would equal 1 over 10 squared, which would equal 0.01. 1 over 100, right, this is 1/100th moles per liter. So here we had 1/10 of a mole per liter. Here we have 1/100th of a mole per liter. So notice that when this exponent gets bigger, this number gets smaller. So as the pH number goes up, the concentration of hydrogen goes down. And that's because of this negative sign here, that exponent ends up being on the bottom of a fraction. So this one is going to be 10 to the negative 3rd. So it looks like it would get bigger because the 3's here, but remember that that means 1 over 10 to the 3rd. And so the bottom of our fraction is getting bigger, which means our number is actually getting smaller, 0.001 moles per liter. And notice that each time we go down a pH point, we are getting 10 times less concentrated because that exponent is on a 10, right? So we were 1 out of 100, we were 1 out of 10, 1 out of 100, 1 out of 1,000, then we'll be 1 out of 10,000. So each time we're kind of diluting it by 10. And if you keep going all the way down here, let's do the 10 one, for example, you would have concentration of hydrogen equals 10 to the negative 10th, which equals 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 1. Okay, so tiny amount of hydrogen here, still, like, again, that's the fraction of a mole, so there would still be a lot of actual molecules, but compared to the amount of water, it's still a pretty small proportion. I mean, it's a super small proportion. Okay, so acidic things have lots of protons. Basic things have fewer. And then let me show you what happens when you get into these negative exponents. I mean, mostly what you need to understand for this class is that there's like acidic things and basic things, and acidic things have more hydrogen and basic things have less hydrogen, and you should be able to use those two formulas to tell me, like, if I gave you a pH, tell me what the concentration of hydrogen was, or if I gave you the concentration of hydrogen to tell me the pH. So like this, what I'm going through right now is like to help you with the conceptual understanding so that it makes sense, so that you're not just like cramming facts into your head, but it's actual, like, you know, you don't have to memorize, but you understand, and so then it sticks better. But okay, so concentration of hydrogen equals 10 to the negative 2. No, I'm sorry, 10. So normally it's 10 to the negative 2, but let me say that again. So concentration of hydrogen equals 10 to the negative pH, right? But if our pH is negative 2, then we have 10 to the negative 2. That means we have 10 to the positive 2, or 100 moles of hydrogen per liter. So that would mean we had more hydrogen than we did water, because our water was only 55.5 moles per liter. So you could have a negative pH if you had a lot of hydrogen. If we did -1, it would be 10 to the negative 1, which is 10 to the 1, which is 10 moles per liter. So that's also a possibility. And if you had 0, concentration of hydrogen equals 10 to the negative 0, which is equal to 10 to the 0, right? Which is 1 moles of hydrogen per liter. So it just keeps going. Like, we're still, as we go up, we have 10 times more hydrogen. As we go down, we have 10 times less hydrogen. But you can keep going into the negative numbers to a certain degree. Okay, I'm gonna clear everything. But yeah, just as like a conceptual thing, like if this whole thing was water, then like a low pH would have like a couple things of hydrogen, and then a medium would have a little more hydrogen, and then a high would have like a lot more hydrogen, except that really you're like going, it would be like factors of 10 times more. It would be like big range of difference in the number of molecules. Whoops. Okay, so let me clear the whiteboard. Whiteboard, clear the whiteboard, clear all drawings. Okay, so the formula that we were just using was concentration of hydrogen equals 10 to the negative pH. And again, that's the one that I like because it's just, I think it just conceptually is easier to think about. The other one is pH equals, hold on, let me think about this. Sorry, I have to convert this just to make sure that I'm doing this right. So if you are familiar with using logarithms, don't worry if you're not, but if you are, this should make sense. Take the log base 10 of both sides. This cancels out with this. This comes down here. Okay, so log base 10 of the concentration of hydrogen equals negative pH, or negative log base 10 equals pH. Okay, yeah. So I thought this was what it was, but I just wanted to make sure, and this is faster than switching out and looking it up online. Okay. See, if you know one of the equations and you're comfortable with logarithms, you can always convert back and forth. Erase. Okay. So the other formula is pH equals negative log base 10 of the concentration of hydrogen. If I give you a problem, I will give you these formulas because you've already seen that my memory is Swiss cheese. So I think it's nice to give people formulas. And I will say, okay, you have a solution. The pH of that solution is 5. What is the concentration of hydrogen? And all you have to do is understand that you need to take this pH number and plug it in where it says pH. And the you could technically use either formula, But when the question mark, when what you want to know is hydrogen, concentration of hydrogen, then use this formula. It's easier to use this formula that has hydrogen all by itself already, so you don't have to do any solving, you just plug in. So concentration of hydrogen equals 10 to the negative 5, and you could leave it at that. You could plug it into your calculator. You could, do the math to figure out what that was as a decimal. But basically just understand like which formula do I plug it into and how do I solve for the other thing. Or I might give you, well, what is pH? You know that your solution has this many hydrogen H pluses in it. It's got the concentration of like a 0.0, and we were just talking about 0.01, 0.001 before, but it doesn't have to be like perfect like that. It could be like 0.053, right? And then, so now, since the question mark is with pH, let me change colors. Orange. Since the question mark is now with pH, then you want to pick the equation that already has pH all by itself on one side, like that. And so we could just plug this in here, negative log base 10 of 0, oh wait, doesn't have to have that square bracket anymore, 0.053. And all you do from there is plug it into your calculator. So usually, if you're doing a calculator, first you would type in 0.053, then you would hit the log base 10 button, or just the log button, and then you would hit the negative sign, because the order of operations, that's what would go first. The log goes first, then you hit the negative. And that would give you whatever number you got out of your calculator. I'm not going to do it. Okay, so those are the two equations, but just basically those two equations are, they're just two different versions of the same thing. So they both allow you to go from this number, like 3, 4, 5, 14, they allow you to go from that number to the concentration of hydrogen that's kind of associated with that. So 10 to the negative 3, 10 to the negative 4, 10 to the negative 14. Okay, so those equations just sort of switch back and forth between that number and that number. And I didn't write that out for 4. Whoops, why is that a 14? 5. You know what I mean. Okay, hopefully that helps explain the pH stuff a little bit better. But yeah. Okay, the other thing was unit conversions. So unit conversions, I would still like to make like a better video on this. There's like, I want to get to like a more advanced unit conversion video. So this will be good. This will be good practice for me to like work out my explanation for how to do this. But let's start with units that people often already know. So we in the United States use the imperial system, or I think they also call it the English system or something, but England doesn't use it anymore, so that's kind of funny. So you know that there are 12 inches in 1 foot, right? So I could have a ruler. My ruler could be 1 foot long or 12 inches long. And I don't know if that was 12, I was trying for 12. That would be equivalent, right? If I say this, it's equivalent, it's equal to this. So you know how, if you have a fraction that's like 5 over 5, that equals 1, or 3 over 3, that equals 1. And you know how, if you take any number and you multiply it by 1, it is equal to the same thing. If you put these ideas together, this idea plus this idea, you get a technique for converting between units by creating a fraction that is equal to 1 and then multiplying by that fraction. So if 1 foot and 12 inches are equal, then if you make a fraction that's 1 foot divided by 12 inches, it's equal to 1, right? Same thing if you do it upside down. 12 inches and 1 foot, if they are equal, then you get another fraction that's equal to 1. So if I multiplied something else by this fraction, I would basically be multiplying that other number by 1, and I would get a value that was equal to the original value, right? Let me show you how that works. Where did my eraser go? Eraser. Y'all wouldn't know that I'm actually kind of an illustrator, but it just is so ugly on the Zoom chat. It's embarrassing. Okay, now what I want to draw. Okay, so here's an example. You need to know, you know that something is 53 inches, and you need to know how many feet that is. One way you can do that is by multiplying by what we call a conversion factor. And a conversion factor is just one of these two fractions over here, for example. A conversion factor has the unit that you already have, so inches, and the unit that you want, and in this case we want to convert it to feet, and it has like an equal number of those two things in the fraction, right? So these are both conversion factors. Here, we want to convert to feet, so we are going to pick the conversion factor with feet on top. I'll show you why. So our fraction here is going to be 1 foot over 12 inches. Now remember, this is equal to 1. So we're kind of saying 53 times 1 equals what? 53 times 1 over 12 is equal to 53 divided by 12. Oh, I should have picked an easier number. Okay, it's not 53 anymore, it's 48. Okay, 48 divided by 12 is equal to 4. So 48 times 1 foot over 12 inches is equal to 4 feet. And I'm trying to think of a way to explain this. The reason that you pick the version that has the number that you want on top is that, remember, when you multiply, like this, okay, hold on. Okay, let's sidestep for a second. Let's make this algebra. Hopefully the algebra doesn't make it worse. Let's say you had this algebra problem and you were asked to simplify it. Well, the x times the y on top would leave the xy on top. The x times nothing, basically like 1 over an invisible 1 over here, would leave the x on the bottom. And this is a fraction equal to 1. So that would actually cancel out and you would be left with just the y on top, right? So if you have, you can treat units like you treat algebraic variables. If you have inches on top and you multiply by feet divided by inches, you would basically end up with like inches times feet divided by inches, but the inches divided by inches is like a fraction that's equal to 1. Inches over inches is 1, because that's like x over x, it's 1. So those would cancel out, and so you would just be left with feet. So you can treat, what do you call these? Units. You can treat units a lot like you would treat an algebraic variable. Let me show you another example. Okay, so we did inches to feet. Let's do feet to yards. So 3 feet equals 1 yard. So we can make 2 conversion factors, right? I'll let you think about what those are for a second. So one of them will have the feet on top. The other one will have the yards on top. And you could have someone say, okay, 9 feet equals how many yards? And you would need to, obviously this one's, I mean, you could do this in your head, but like if this was harder, you couldn't, right? So this, it's an easy example to work on, but you won't always be able to do it in your head. So we need our conversion factor right here, and we have feet, we want yards, so we're gonna pick the conversion factor that has yards on top so that we end up with yards at the end. So not this one, it doesn't have yards on top, this one. So again, this is a fraction equal to 1. 1 yard is the same thing as 3 feet. So if we multiply 9 feet times this number, we get something that's just as long as 9 feet. And we're going to do 9 times 1 is 9, but then divided by, 9 times 1 divided by 3. So 9 times 1/3, I guess is the best way to think about that. So 3. And this feet that's on top and this feet that's on the bottom, those are going to cancel each other out because foot divided by foot is 1. Okay. Alternately, I could say 4 yards equals how many feet? And then I would pick the other conversion factor because I want feet now. So I'd say 4 yards times 3 feet per yard equals 12 feet because the foot stays, but the yards are going to cancel each other out. And then clear on my drawings. A lot of the time, you will use these unit conversions to go from metric units, from one metric unit to another metric unit. So let's say I wanted to go like the easy way, right? Is like, okay, 10, now let's say 17 meters equals, wait, give myself some room, equals how many kilometers? Well, I know that there are 1,000 meters per 1 kilometer. So that's one possible conversion factor, or I could flip it upside down. 1 kilometer per 1,000 meters. Okay, that looks good. So now I'm half meters. I want kilometers. I'm going to pick the one with kilometers on top. So I'm going to pick this one. 17 meters times 1 kilometer over 1,000 meters equals 17 divided by 1,000, or what would that be? 0.17, I think? No, maybe one more zero in there. 17, 1, 2, 3. Nope, that looks good. Okay. Yeah, so, and then the meters cancel, right? So that's how you use the conversion factors to multiply back and forth. There's a slightly harder kind of problem where, let's say I wanted you to go from like 83 centimeters, and then you were supposed to convert that into like, let's go back to kilometers. 83 centimeters equals how many kilometers? You might not know off of the top of your head how many centimeters are in a kilometer. Like you probably know how many centimeters are in a meter, and you probably know how many meters are in a kilometer, but you might not be able to go straight from centimeters to kilometer. There's kind of 2 ways you can do this. You could convert to meters first, because meters is the one that you know. So you could say, all right, there's 100 centimeters in 1 meter. So there's 0.83 meters, and then I need to convert that to kilometers. Well, now I can do another conversion factor. I know that there's 1,000 meters in a kilometer. And so then you would figure out that that's 1, 2, 3, 8, 3 kilometers. That's 83 centimeters is equal to this, I think. So really all we did here was just like convert to meters because meters are like point of reference, and then convert to kilometers. So doing it in 2 steps is okay. The other thing you can do, this is a little harder and I'm worried that I'm not going to do a good job of explaining it. How do I want to explain this? Yeah, I don't think I'm going to do a good job of explaining the other way. What is the other way? There's a way that you can do it in 1 step that I like to do it in 2 steps. So that's part of the reason that I'm drawing a blank here. Let me think for a second. 83 centimeters times, if I said, well, okay. I'll show you a different, hold on. So there's that table that you saw that goes like meter, and then it's like, excuse me, like a decimeter, which is like 1/10 of a meter, and then a centimeter, and then going this way, it's like a decameter, and I forget this one again, hecameter, hecta. We had this conversation, what was it? And then there was a kilometer. But there's all those rows in the table. You could say, all right, this is 83 centimeters. I'm going to get like 10 times smaller as I go up. So you could think, okay, well, 8.3, 0.83, 0.083, 0.0083, 0.00083, or vice versa. If I told you there was 57 kilometers, you could say, oh, there's 570, whatever those are, hectometers or whatever. Then there's 5,700 decameters, and then there's 57,000 meters. That makes sense, right? Kilometers would have 57,000 meters. And then there's 570,000 decimeters, and then there's 5,700,000 centimeters. So you can kind of count like, okay, we're jumping 1, 2, 3, 4, 5 places up. We're going to move the decimal 1, 2, 3, 4, 5 places that way. Or we're going 1, 2, 3, 4, 5 places down. We're going to move the decimal 5 places the other direction. Anyway, okay. Sorry, again, I know that may not be super clear, but that is what I have available to you in terms of ways to explain it. So I'll keep working on developing a better explanation for that. Let me know if you have any feedback. And sorry again for not having it all pulled together during lecture, but I hope this helps. Have a great night, everybody.